Hi folks, welcome to this lesson on graphs of functions and their derivatives. In the last lesson we found the actual equations of a derivative. Remember, a derivative just catalogs the slope of the original one anywhere. But sometimes doing that with lim as h goes to 0 can be cumbersome, finding the actual equation. And so we could just look at what's the relationship between the graph of a function and its derivative. And to do that, we could start by just cataloging the slope on some function. So let's call this function f of x. And it's asking us to find f prime at negative 3. That means the tangent slope, because f prime means tangent slope, at negative 3. Well, let me go through this function. It's, kind of a roller coaster. We're going up here. If I were to draw the tangent at negative 3, I think it looks kind of like maybe like this. And if I were to just estimate its slope, here's a point I can see on the tangent. Here's another point on the curve. I mean, roughly its slope is about 4. There's about 4 rise for every 1 run. So I could say it's 4-ish. And that would seem reasonable. Now, if I tried to find the tangent slope at x equals 0, let's imagine we're going through this function. We get to the top here, or this roller coaster. The tangent right at the top would be horizontal. So that's a slope of 0. Horizontal line has a slope of 0. I don't think I need to put ish there, because 0 really is horizontal. And I can just go through and catalog some more slopes. So let's check it out right here. If I were to draw in the tangent, I don't know, it might look like this. There's where it touches. Here's another point I can see, just 1 over. I think the slope there between them is about negative 2. Like it went down about 2 blocks for every one it went over. So I'm going to say negative 2-ish. And I'll find some more slopes by just estimating what the tangent looks like. So the tangent at 0, I don't know, might look something like this. Seems reasonable. Okay. And it looks like it has a slope of down 3 over 1, about negative 3-ish. Now your tangent might look a touch different, and that's okay. We're just making estimates here. But the tangent at 0 should probably be steeper than the tangent was at negative 1. Let's keep going through this. If I go to x equals 1 and draw the tangent, I can see it is somewhat less steep than it was at 0. Okay, so here's where it touches. And I don't know, here's another point. Between those, it's gone down to about and over 1. So negative 2-ish. And at x equals 2, I've got another one of these turning points. So the tangent slope there is 0 if I were just to draw the tangent. And the tangent just sort of represents the direction of that graph in that instant. One way to think about the tangent is if you had a ball or a marble that was running around this track, and it followed the track, and then suddenly, right here, the rest of the track just disappeared. Okay. What direction would that ball roll off in? Well, it would roll off in the direction that it was right at the instant the track disappears. It would probably go like this. There's the tangent slope, or the tangent drawn in. Let's get rid of all of this, because there's just one more we're supposed to estimate. At 3, I'm going to draw in the tangent slope there. I don't know, I'm just making a little estimate here. I think between 2 points, it's gone maybe up 1, 2, 3, 4-ish again. Yeah, and over 1. So if I were to graph all those points, then I'd have what the derivative looks like. So at negative 3, there's a slope of 4. At negative 2, there's a slope of 0. At negative 1, there's a slope of about negative 2. Negative 3, there's a slope of, or at 0, there's a slope of about negative 3. At 1, there's a slope of about negative 2. Here there's a slope of about 0, and here it's 4. And I could connect those up smoothly. And I could use that red graph to just estimate the slope of the purple one at any point without having its equation. Okay? And I'm just assuming that it's connected smoothly because the original one was a smooth function. That's a kind of laborious way of finding the graph of the derivative. So you can do some questions around that on the Stewart sheet that is probably in the Google Classroom, just number 1 and 2. But you should also think about what were the most important points on this. And if it were me, and I was thinking about the most important points, it's important to know what happens to the far right and the far left. It's important to know when the slope is 0. And it's important to know when the slope is at its steepest. Okay? And it's steepest right at the origin here. If you were on this roller coaster, that's where it's going to be at its steepest, between those slopes of 0. Hopefully you've had some time to do some of those practice questions. And now let's look at sort of how the graphs of f and f prime are related to each other. If f is decreasing, so let's just draw a decreasing function. If a function is decreasing, its slopes are negative. Those are identical meanings to each other. If it's decreasing, the slope's negative. And then it's worth saying, okay, that means the graph of f prime is going to be below the x-axis because it's a negative value. If the slope is horizontal, then we've got f prime equal to 0. And that's where the magic might happen on the graph. You might have a turning point. And if the slope is increasing, so if the function's increasing rather, so if I had a function like this, well then the slope has to be positive everywhere on that. So these become definitions for each other. A positive slope and an increasing function are the same thing. We're going to draw 5 more derivatives, but we're probably going to do it with less work than we did on that first one. And we're really going to zero in on these most important points. We care about vertices. If they're smooth, then slope of 0 at those points. We're going to look for steepest points, especially between vertices or turning points. And we want to know what happens to the far left and the far right. So let's check out this first one. To the far left, this has a steep negative slope. So its derivative is going to be at x equals, let's see, this is at x equals -3, or what we're considering the far left here. Its derivative is going to be a big negative value. How big? Doesn't really matter. I'm just estimating here because I want the general shape. Are we going to get exactly the right numbers? No, we're not, and that's okay. If I think about this point over here, the far right, it's got a steep, I could draw it in, a steep positive slope at that point. So let's say that. Steep positive slope at x equals 3. So, I mean, I could draw a point on the derivative. Maybe I'll make the derivative in black. It's going to be a big positive value. How big? I don't really know. Now, in between those, right here, we have a turning point. And it's a smooth turning point. It has slope of 0. Okay, because it's horizontal at that turning point. So let's just catalog that. Slope of 0. Okay. So this is telling us the slope to the far left is a big negative. The slope at 0, at the turning point, is 0. And the slope to the far right is going to be a big positive number because it gets steep and positive to the far right. Get rid of those. Let's just connect this up. I don't exactly know how it should be connected, but maybe it's linear. If you did it as something that looks kind of like a cubic, Guess that would be okay for now. We don't really have a whole lot of other insights into how it's going to all shape up. Let's repeat the process over here. So again, we're looking what's happening to the far left and far right. Okay, so over here, this is steep and positive. So that means it's got a big derivative value there. And right over here to the far right, it is also steep and positive. So it's going to have a big positive derivative value. There we go. We've dealt with far left and far right. The next most important points are going to be places where we have slopes of 0. And that would be at the turning point. Slope of 0. And slope of 0. So let's catalog that. At those x values, at the x value of -2, there's a slope of 0. Because the derivative is just telling us the slope of the original. At x equals 2, the slope is 0. And here comes the next, or the other most important one. Over this interval between those slopes of 0, where is it steepest? Oh, right here. Okay. That's where it's steepest on that interval. Negative slope. Okay. So I don't know exactly how low down it goes. It doesn't look like it's as steep as it was for the other points around x equals 4 or 5. But it's definitely negative, and whatever you choose it to be, that's as low as slope goes. And now that we've got that, again, your values might be slightly different. I'm just going to try and connect these up as smoothly as I can. As long as you have something that is roughly in this shape, and that has those zeros, or x-intercepts at -2 and 2, then you've got a reasonable look at the derivative. 3 more. Right here, the slope is positive. Okay, it's a big positive value. Right here, the slope is a big positive value. Where is slope 0? Where are the turning points? Well, right here, right here, right here, and right here. So slope is 0 at those chunks. Okay, maybe I'll do the actual points on the derivative in black. And then throughout those intervals between the slopes of 0, it's at its steepest negative right here. Okay, so big negative value. It's at its steepest positive right here between the next pair. So if we went on this little section, so a big positive value. And we've got steepest negative again here. And that's a bunch of points. Let's just try and connect them up smoothly. Now these graphs should look somewhat familiar. The purple graph, I think, let's go a little bit darker here. I think the original one looks a lot like sine x. The black graph, I think, looks suspiciously like cos x. Now this is not a proof that the derivative of sine x is cos x, but it's strong graphical indication. Okay. So we looked at the far left, far right, we looked for slopes of 0, and we also looked at steepest points in between. All that red stuff was just stuff to help us find some of those values. Now what happens if we don't have any turning points? Well, I guess we're just going to have to catalog some slopes. So right here, I mean, the far left, it only goes this far left. Right there, that is really steep and positive. Right here, if I drew in the tangent, I mean, it's kind of medium steep and positive. So I don't know, its derivative will be not too small. Right here, it is less steep, but still positive. So I guess maybe down like this. get rid of some of this red stuff. And, I mean, if we went over some more, if we ever get confused, just use more points. It is still positive, but not very steep at all. And if I connect all that up, I get something like this. And again, this might give us some graphical evidence for a common graph. The original function here might be, let's get it in purple, might be ln x, or the natural logarithm of x. The black one, you might have some guesses, but it looks like a piece of 1 over x. Okay, just the right-hand piece of it. That's our guess. Is the derivative of ln x 1 over x? It turns out it is. There's some graphical sort of indication, but again, that's not a proof. And lastly, we're going to look at a function like this. Now, it should actually connect up like this. Okay. So on this function, if I looked at the slope here, the slope, I can actually tell the slope is 1 there. The slope right here is 1. The slope here is 1. Okay. The slope here is 1. The slope here is 1. So it's always 1 on this absolute value graph. And if I looked at the other side, well, the slope here is negative 1. The slope here is negative 1. The slope here is negative 1. It's always going down 1 and over 1. Slope here is still negative 1. The question is, what is the slope exactly at 0? You might say that the slope is 0, but it actually doesn't come to a soft landing towards a slope of 0. It's just boom, negative 1 from one side, and boom, positive 1 from the other side. It's a sharp point. And what we can say about the slope there is that we have no idea what it is, because it is different from each side. Think about our limit definitions. We always want the limit to be the same from each side, and if it's not, then we have trouble. Our derivatives come from limits. So lim as h goes to 0 should be h going to 0 from both sides. This function has different definitions from each side. So we can say here slope is undefined, or tangent slope is undefined at x equals 0. Okay. So if you end up with sort of these piecewise chunks or places where you have sharp points, then you're going to have open dots in your derivative because the derivative is not defined there. What does that mean algebraically? Well, we may take a look at that a little bit later. But you could just say that f prime is going to be 1, where x is greater than 0, and negative 1, where x is less than 0, and undefined at x equals 0. There is a sheet in the Google Classroom that's from the James Stewart book, and you can take a look at that, numbers 3 to 10. And we're just drawing and matching some graphs and their derivatives. I hope this has been helpful. Good luck with the material, folks, and take care.